Swayam Prabha. Digital India. Educated India.
Good morning. We will continue our discussion of linear instability analysis, and we will start by quickly recapping what we did the last time. We wrote down a series of steps that we go through to start with an equilibrium solution, and then we develop a linearized version of the governing equations about the equilibrium solution. So, what this does is it helps us understand the behavior of a small perturbation around the equilibrium solution. Now, if the equilibrium solution happens to be a constant, like the case that we discussed, the dispersion relation can be obtained in closed form. If not, one would have to solve for these eigenvalues. Essentially, the dispersion relation gives us the eigenvalues at any point in time. If the equilibrium solution is not a constant, one would have to solve for those eigenvalues numerically. Say for example, you look at if I can apply the same exact methodology to look at the stability of the parabolic velocity profile in a round pipe. Okay, when I take u equal to some 1 over r square over capital R squared, which is like my parabolic velocity profile, it is not a constant in R, it is not a constant in space. Essentially the mean, the equilibrium solution is not a constant. Therefore, what we end up with is a fourth order ordinary differential equation that and an eigenvalue problem involving this fourth order ordinary differential equation which governs the growth or decay of the perturbation quantities. That fourth order equation is very often called the Orr-Sommerfeld equation. Okay, so, essentially the Orr-Sommerfeld equation is obtained through exactly the same process, except in that case you would have to solve for the eigenvalue with the largest real part, which is going to determine the growth of a given perturbation numerically. Whereas, in this case we are able to obtain it in closed form, meaning analytically, because the mean flow is simply a constant. Okay. Now, I do want to show that this is not something that is that came out of the whim or fancy of a mathematician's mind. This process of obtaining the most unstable wave number. So, essentially if we go back to this dispersion relation, it is some omega is a function of k, omega is the growth rate, also in mathematical terms you would call that the eigenvalue, k is the wave number. This growth rate as a function of the wave number is some algebraic equation. In our case it turned out to be a polynomial, but in general it could be any algebraic equation, explicit, in some instances even implicit, but it is a closed form solution that if I give you a k, you can give me an omega, and it could be not one omega or two omegas, but many omegas. If omega happens to be a transcendental equation, if this equation happens to be a transcendental equation, but the one eigenvalue that I am interested in is the one with the largest real part. For that k, it is that one eigenvalue that is going to govern the growth of that disturbance. Now, so from this we can find at one particular value, I will call this k 0, k 0 is the what we would often call the most destructive wave number, which means that for a given disturbance of this wave number k 0, the growth rate omega, the corresponding growth rate omega 0 is the maximum of all the possible growth rates for all the other wave numbers. Okay, which means because of the functional form e power omega t, this particular wave number is going to appear to grow the fastest in relation to all other wave numbers. And this has been validated experimentally in many situations. Like the example that we just solved, you can show for yourself that when the water you can go back to the dispersion relation that we solved. So, if you replace the what we call fluid number 1 with air and the fluid number 2 with water, and also set sigma to be equal to the surface tension of water, you will find that the lambda 0 corresponding to k 0 is on the order of about 10 centimeters, 7 to 10 centimeters. So, that is when air is blowing over a lake that is otherwise at rest and air is blowing at a velocity of 10 meters per second, the ripples that we observe, this theory predicts, will be about 7 centimeters in wavelength. Okay. This kind of a prediction can obviously be very easily validated in experiments, and it has been validated. Okay. Now, what we want to do is look at how this theory can be applied to sprays and atomization, which is what we are after. Now, so if I take the first instance of an atomization problem, if I take a cylindrical jet ensuing out of a nozzle of radius r, okay. I am going to assume, so this is now the case of an axisymmetric flow. I am going to assume rho 1 and u 1 are the density and velocity of the fluid outside, rho 2 and u 2 are the density and velocity of the fluid of the liquid itself. So, imagine just a water faucet, a faucet through which a jet of diameter 2 r is exiting into, let us say, air. Okay, the air is at some velocity u 1 and the fluid is at some other velocity u 2. Now, what we do actually end up considering is not this problem, but the case of an infinite cylindrical jet. So, if I replace this with an idealized problem, that is infinite in the z direction. I can go through the exact same process, that is step 1, write the governing equations, I will use the subscript notation I. Like in our old notation, we said capital quantities are the mean flow quantities, and in this case u I happens to be a constant, u 1 and u 2 both are constant in their domain of definition. So, if I now simplify this equation, u d u I dx is 0 because it is not a function of x, and du dt is also 0, which implies, just like we found in the other case, du dx. Well, in this case I should write not x, but z, because okay, what we can show from this is, if I write the same equation in the r direction, what we find is that P I is a constant, except if you remember in the flat interface problem, we found that because the interface curvature was 0, P I P 1 is also equal to P 2. So, the pressure in both the fluids put together was a constant. We will see here that because you have this interface having a curvature. So, if this happens to be a round jet in cross section, and the radius of that round jet is this capital R. So, what we find is that P 2 minus P 1 is equal to the sigma over capital R. So, at the mean flow condition, the capital P 2, which is the pressure inside the liquid, is constant inside the liquid. P 1 is the pressure in the fluid outside, that is in itself constant, but P 2 minus P 1 has to be equal to this sigma over R, because of the surface tension pressure that occurs at the interface. So, let us just make sure we understand this, understand the physics of how this comes about. If I take a piece of that some delta theta in diameter in angle, if I take a piece of the jet, and if P 1 happens to be the pressure, P 2 happens to be the pressure here, and P 1 happens to be the pressure outside, there is a surface tension force that acts at the cut section. So, if I cut the fluid at some point here and here, there is a surface tension force that acts in either direction, and this surface tension force has a component in this direction and a component in this direction. What you will find is that this P 2 minus P 1 has to be sufficient to balance the normal component of these forces. The vertical component, as shown in this figure, will cancel out. Okay. And from that you get this curvature dependence. So, if I take this angle, the sine and the cosine, essentially if I say that the normal component of this force, which is this force, is a function of this delta theta, and therefore, you start to get these curvature effects. So, if I take the perturbation quantities, if I write u as the u bar I plus u I vector, u is the total velocity field, u I is the mean velocity field, mean, or I would like to call it the equilibrium velocity field. and this is my perturbation component. If I go through the same process that I went through before and linearize these equations, I will keep these in the vector notation just to sort of make things a little easy for us. From continuity equation, what we find is that del dot u I is equal to 0. This says that the perturbation velocity field is also divergence free, meaning the perturbation velocity field has to instantaneously obey this incompressibility condition. Essentially, del dot u being 0 is coming from the fact that the fluid is incompressible. And so, if these are now the linearized equations that I am writing. I do not want to go through the same process of showing you how I substitute the mean plus perturbation into the full governing equations, take out all the order epsilon squared terms, keep only the order epsilon terms, and that is when you get these linearized equations. Okay. So, I am skipping those two steps in the interest of time to just show you the equations that you get from this linearization. First equation is del dot u equal to 0. And the second equation so, if I take the total pressure to be equal to this P I plus little p I, just like we wrote in the previous case, okay. So, if I now take, I will mark these now as equations 1 and 2. If I take divergence of equation 2, and if I use equation 1, what we end up getting is this equation del dot grad of P I, the divergence of gradient of the pressure in each of the fluids is 0, which can also be written as del squared P I equal to 0. Now, del squared is a linear operator, So, I will just sort of write this out in open form. This is our equation that we get from just combining the system of linear equations that we have. Now, I want to point out one thing here that will reinforce some of the concepts that we discussed in the earlier linear instability analysis. At this stage, we introduced what we call the normal mode expansion, correct. We said we will write Pi as as e power omega t plus I k z plus I m theta. In the previous case we did not have this I m theta. In this case I have two spatial variables over which the perturbation can vary in the z direction as well as the theta direction. We will see what this means in just a moment, but essentially I am assuming that my perturbation has two spatial variable forms, two spatial variables involved and one time variable, and if I do that I have this, and of course I have the pre multiplier this p prime I of r is what we said would be the eigen function in the r direction. Now, this is what we call the normal mode expansion. What I want to show you is that really speaking you do not even need to think of that as an assumption. The normal mode expansion is not an assumption that we make. I will show you how. If I look at equation 3, so we want to answer where does this come from. We in the previous analysis I showed this to you as though it was an assumption, but I want to show you that it is really not an assumption, that there is a fairly simple procedure to obtain it. So, if I look at equation 3 is the Laplace equation in 3 dimensions. So, this is if I replace this P I with capital T for temperature, it is standard heat conduction equation in cylindrical polar coordinates, steady state heat conduction equation in cylindrical polar coordinates. How would you solve that equation? You have to first identify which are the homogeneous directions and which is the direction in which you may have some sort of an inhomogeneity, right. In this particular instance, z is a coordinate in the vertical direction. So, the z coordinate basically is infinite. The theta coordinate is a periodic coordinate. So, clearly those are the two directions in which the coordinate has homogeneous boundary condition, homogeneous or periodic, really I should be saying periodic boundary conditions, right. So, if I simply do a separation of variables solution on equation 3. So, if I say P I of r theta z and time is equal to r of r comma t times theta of, I am going to write this as capital theta of theta comma t times capital Z of z comma t. In fact, we do not even need the t in every one of these. I will show you in a moment that even that is not required, times some capital T of t. If I take this assumption, which is essentially coming from separation of variables, okay, and I introduce that into the governing equation, okay, what I will end up seeing here is